Life cycle of a device or hardware. A green device cannot be built by just having an additional step in the life cycle of the device. There needs to be a concerted effort at every stage of the device life cycle, from the moment the device is conceived, to its development, to the time when it is used and recycled or disposed, i.e. from cradle to grave. Each stage of the cycle has varying levels of impact on the environment. In this section, we will look into each stage that a computer device goes through and discuss green considerations for each stage. The typical life cycle of a device, shown in figure, it consists of 5 stages. 1. Design. 2. Manufacture and facilities. 3. Packaging and transportation. 4. Usage. 5. Reuse or disposal. Design. In the design stage, the idea is conceptualized and the device is designed, prototyped and tested. Though this stage does not have direct impact on the environment, design stage decisions such as those regarding architecture, constituent components or materials and layout have a huge effect on the environmental impact of other stages. Hence, it is important to design devices so as to keep their environmental impact as low as possible during subsequent stages whilst meeting performance and other requirements. We will look at a possible process improvement that will help design a green device. Figure shows the typical steps in the design process. When a device gets into the design stage, the first step should be to set environment targets for it. Samsung, 2011. As indicated in figure, setting environmental targets should be done in parallel to conceptualization. These targets can be derived from the device's environmental objectives, and also based on environmental impact assessment reports of similar devices that are in the market. These form a minimum set of targets that the device has to meet when released to the market. These targets should act as a benchmark and should help with decision-making whilst designing the device. As the device is being prototyped, one of the goals should be to meet all environment targets that have been set. To achieve this, we need to continuously assess the prototype's design and improve it until the targets are achieved. To assess and improve the prototype, we need to take a holistic approach to the device's life cycle. Sustainability Victoria. As shown in figure, we first need to map the device's entire life cycle to understand the places where we perceive and estimate its environmental impact. This assessment should include each stage of the life cycle from manufacturing and transportation to usage and disposal. Effort should be made to quantify the impact at every stage of the life cycle. This will help us identify main sources of environmental impact. Design alternatives to reduce the environmental impact need to be considered. Design changes have to be implemented and the prototype has to be assessed again for environmental impact. This process should go on until the device meets the environmental targets set for the device.
Manufacturing. The manufacturing process is one of the main sources of environmental impact in the life cycle of a device. Manufacturing processes are resource-intensive and consume a lot of raw materials, water and energy. They create many different categories of waste, some which are toxic. For instance, according to a UN report, production of a desktop personal computer, PC, consumes 240 kilograms of fossil fuels, 22 kilograms of chemicals, which includes hazardous chemicals, and 1.5 tons of water. United Nations Environment Programme, 2004. It is very important to minimize the use of environmentally sensitive substances and reduce the amount of harmful waste. The EPEAT, Electronic Product Environmental Assessment Tool, (ND) rating system serves as a good guideline for understanding how green a device is. EPEAT grades electronic devices and computer systems into 3 grades: bronze, silver and gold. Helps customers identify how green a device is and helps them to make informed choices. The rating system takes into account the following aspects: reduction or elimination of environmentally sensitive materials, material selection, design for end of life, device longevity or life extension, energy conservation, end of life management, corporate performance. Packaging. Since it covers most aspects of a manufacturing process, it serves as a good way to assess the greenness of a device with respect to its manufacturing. Electronic devices may contain hazardous and environmentally sensitive materials like lead, Pb, cadmium, Cd, mercury, Hg, hexavalent chromium, Cr6+, polybrominated biphenyls, PBBs, polybrominated diphenyl ethers, PBDEs, arsenic and polyvinyl chloride, PVC. It is important to reduce, if not eliminate, these materials both in the device and in its manufacturing process. The Restriction of Hazardous Substances, RoHS, ND, directive restricts the hazardous substances commonly used in electronics and electronic equipment. Lead is generally used in printed circuit boards and in glass monitors. The pathological effects of lead are most prominent in the nervous system, hematopoietic system and kidneys. Excessive exposure to lead, Pb, results in clinical toxicity. There has been extensive research to find a replacement for lead, Norwegian University of Science and Technology, 2010. There are also ongoing efforts to recover lead from the e-waste, Duffy, 2008. Cadmium is generally used in low-temperature soldering, plating for corrosion protection, colorants in plastics and contact buttons in relays, Pinnaca and Hilti, 2004. Cadmium when ingested affects the liver and kidneys. Research is ongoing to produce alternatives for its various uses. Mercury is mainly used in monitors and batteries. Mercury is a well-known pollutant, U.S. Geological Survey, 2000, and it affects the immune system, alters genetic and enzyme systems and damages the nervous system. New light-emitting diode, LED, backlit technologies have been developed which make monitors mercury-free. Mercury use in batteries has also been reduced considerably over the past few years. PBDs and PBBs are used as flame retardants, Wisconsin Department of Natural Resources, 2011. These materials are ubiquitous environmental pollutants. They are extremely toxic and are banned in many countries. Efforts are ongoing to remove these materials from the manufacture of computers. Arsenic is used in glasses and in manufacturing semiconductors. Arsenic interferes with cellular longevity by allosteric inhibition of an essential metabolic enzyme. Many arsenic prevention and recovery methodologies have been devised, and these need to be actively deployed to reduce arsenic usage in the manufacturing process. PVC is one of the most commonly used plastics worldwide. It has been used extensively in the manufacture of computer parts. Vinyl chloride, one of the main ingredients of PVC, is a carcinogen and also affects the human reproductive system, U.S. Environmental Protection Agency, EPA, 2011. Of late, many companies have eliminated the use of PVC in their devices. The EPA website gives further information on these and other toxic materials and how each of these chemicals affects the environment. It is important that electronic device manufacturers avoid using these chemicals in their devices and use environmentally friendly alternatives. Further, their facilities' carbon footprint can be reduced by employing energy conservation techniques and by using energy from renewable sources. Energy conservation techniques like sensors for switching off lights automatically, and shutting down servers during weekends, where possible, not only help reduce the carbon footprint but also result in lower energy bills. In addition, environmentally sensitive materials like chlorofluorocarbons, CFCs, should be avoided in air conditioning and cooling facilities. Such measures also help companies in projecting a good public image. Packaging and transportation. Packaging and transportation also contribute to the carbon footprint in a device's life cycle. The two main contributors in this segment are the materials used for packaging and the carbon footprint of the vehicles used in transportation. Since the materials used in packaging a device have an effect on the device's carbon footprint, the amount of material used for packaging needs to be kept at a minimum. The packaging should be done in such a way that it minimizes the amount of material used whilst ensuring the integrity and security of the device. The size of the device has an effect on the amount of packaging required, so even during the design stage, effort must be made to make the device as compact as possible. Eco-friendly materials like recycled paper, potato starch and recycled board can be used as packaging materials, and soy ink can be used for printing. The following are general recommendations for designing suitable packaging. U.S. Environmental Protection Agency, 2011. 1. Packaging materials should be recyclable. 2. The amount of packaging materials should be kept at a minimum. 3. Various materials used in packaging should be easily separable to ease the recycling process. 4. Adhesive use should be reduced by using folds and tabs instead. 5. All the additives, coatings and inks that get added to the package should be eco-friendly. 6. Printed documentation can be avoided wherever possible. Instead, documentation could be provided through the device's web page. In addition, freight transportation leads to a lot of carbon emission. Along with making the transport system efficient, the design of the device should facilitate smarter transportation. For example, the smaller the device, the more of them can be transported in a given space, thus reducing the number of vehicles required to transport them from manufacturing facilities to distribution centers. Use. Quite a significant amount of energy is consumed by devices when they are being used, powered. This increases a device's carbon footprint, thus resulting in a profound impact on the environment. The Energy Star rating system helps customers choose the most energy-efficient devices and, thereby, reduce their energy consumption and cost. Often people tend to apply a usage pattern without being aware of a device's characteristic. For example, the commonly held belief that, to ensure longer life of a battery, the battery needs to be drained completely before recharging is not necessarily true for all battery types. In case of lithium-ion batteries, commonly known as Li-ion batteries, the maximum number of charge cycles decreases with increase in depth of discharge. Buckman, 2011. Since the best usage patterns are tightly tied with a device's characteristics, it is important that manufacturers provide guidelines on its best usage practices from environmental and energy perspectives. Devices like Kilowatt, P3 International, 2011, help measure the amount of energy consumed by a device over time. When Kilowatt is plugged between the device and the power socket, it measures the amount of energy that the device consumes. This can be used to measure the amount of energy consumed over time and with different configurations of the device, and thus helps one find an optimum configuration that consumes the least energy. It also helps one figure out whether older devices are still energy efficient. The amount of energy consumed by different kinds of electronic devices varies widely, and ways to reduce their energy use vary widely too. Hence we will look into different device categories separately, and look at ways to reduce energy usage in notebook computers, desktop computers, servers, mobile devices and other special devices. Notebook computers. Though notebook computers are designed to be energy economical compared to desktops, the energy consumption of a laptop depends on the usage pattern. To reduce energy consumption, it is necessary to have a usage pattern that results in optimal energy consumption. Let's examine the power consumption of a laptop's different components and discuss how each component's power consumption could be reduced or optimized. Notebook computers are generally powered by a rechargeable battery, which when in good condition powers the device for about 3 to 5 hours. The battery is recharged with the help of a charger, which can charge the battery irrespective of whether the device is running or is in a powered-down state. The lifetime of a battery is generally short, they last for only about 300 to 600 charge cycles. This results in the need to replace the battery a few times during the life of a laptop, thereby contributing to e-waste. A few companies are also coming out with notebook computers which run on solar power. Notebook computers are also characterized by their liquid crystal display (LCD) or LED monitors, which are integrated into the device. The monitors and CPU consume the largest share of power that is utilized by the laptop. Mesri and Vardan, 2005, Robertson et al., 2012. The larger the monitors, the greater the laptop's power consumption, Albert, 2009, and the more intensive the operations performed by the processor, the higher its power consumption. Energy can be conserved in a laptop in several ways. According to various studies, quite a lot of the energy wasted in a laptop happens when the laptop is being charged. Snyder, 2009. The chargers convert the AC to DC and steps down the voltage. This happens as long as the charger is connected to the power socket, irrespective of whether the laptop is connected to the charger or not, thus resulting in wasted energy. Hence it is important to switch off the power supply and unplug the charger from the power socket when it is not in use. This will reduce power wastage. Of late there have also been green chargers, such as the iGo Green Charger, available which can detect whether a charger is connected to a notebook computer or any other device, and reduce the power consumption when a charger is not connected to a device. Monitors consume about 20 to 30%, Mesri and Vardan, 2005, of the total energy used by a laptop, hence it is important to reduce their power consumption. Strategies that help in reducing their power consumption include the following. 1. Reduce the brightness of the monitor to an appropriate level. A brighter screen consumes more energy. 2. When some background task is running on the computer and there is no need to use the monitor during this time, switch off the monitor instead of using screensavers, as screensavers also consume some energy. 3. Most computer operating systems provide power-saving profiles which, when enabled, reduce the amount of energy consumed by the computer. For example, when the laptop is starting up or shutting down, these applications reduce screen brightness to a minimum. Laptop processors also consume a lot of power, particularly when carrying out computationally intensive tasks such as encryption, analytics, computer games and image and video processing. Many aspects of applications that run on a system impact power consumption. The following guidelines will help in optimizing energy consumption. 1. The background processes and other applications which are not being used are kept running to keep the processor active, thus resulting in energy wastage. So when an application is not in use, close the application and also stop the background processes that are not being used. 2. Multitasking is a trade-off between CPU time spent executing tasks and inefficiencies brought in by context switching. When a task starts running slower than it would normally run, one of the likely causes is due to inefficiencies due to context switching. It is advisable to reduce the number of tasks when such slowing down is noticed. 3. The more processes that are set to start at startup, the longer amount of time the laptop needs to boot up, thus resulting in more unproductive time for the processor and the monitor. So keep the number of processes at startup to a minimum. The required applications can be started when needed. 4. When playing games or other multimedia applications, the greater the level of detail, the greater the processing power consumed. So it is better to keep the level of detail to the required level. Most games support this feature. The higher the speed at which a processor runs, the more energy is consumed, so advanced users could run the processor at a lower frequency, that is underclocking it, to save power. This can be done by going to the basic input-output system, BIOS, of the laptop and setting the appropriate processor speed. In most computers, going to the BIOS is easy, though it depends on the computer configuration. In contrast, if a computer is perceived to be slow and you are contemplating replacing the processor, a better option would be to try overclocking the processor to see whether the increased speed meets the need. Overclocking a processor can harm the computer, so practice caution and have a computer expert do it. In addition, multi-core processors consume relatively less energy for the same amount of processing done by multiple single-core processors. This is primarily because of the decreased power required to drive signals external to the chip. The other major component of the laptop that consumes a lot of power is the hard disk. Since hard disks are physical devices, they consume relatively more energy than many other components. Hence, it is important to keep hard disk access to a minimum and use it only when necessary. The spinning of the hard disk is one of the important parts that results in higher energy usage. Lessening the spin of the hard disk results in lower energy consumption. The spin of the disk is greater when the files are fragmented and scattered all over the hard disk. Defragmenting the hard disk reduces the spin of the hard disk and will result in less energy usage. Solid-state drives, SSDs, are known to consume less energy than comparable hard disk drives, HDDs. In addition, many power-saving options are available on computers that switch off the hard disk when it is not in use. For detailed coverage of energy-efficient, environmentally friendly computer storage, refer to Chapter 6. Peripheral devices connected to a computer also consume energy, even though they might not be in active use. For example, devices connected to USB ports in a computer draw power even when the device is not in use. So when these external devices are not in use, it is better to unplug them. Most notebook computers can operate in at least 2 idle power modes, standby and hibernate. These modes help keep the laptop's energy consumption to a minimum whilst still retaining the state of the computer. In standby mode, the laptop's internal devices and optical drives are powered off, but the power is still maintained to the RAM, where the state of the device is preserved to facilitate instant resumption. Though this state requires considerably less power compared to when the computer is running, it still requires some power, which needs to be supplied by the battery or an external power source, or else the system will shut down immediately, thus losing the state. Retaining the state is very helpful when we are away from the computer for a short period of time. The hibernate mode makes the laptop completely shut down whilst still retaining the powered-on state, thus reducing the startup time. When a laptop goes to hibernate mode, the current state of the machine is stored in the hard disk, and all the devices including the RAM are powered off. When the computer is resumed from this state, the state information from the hard disk is reloaded into RAM. It takes more time to resume from hibernate mode than from standby mode, but it is more energy efficient. This mode can be used when the state of the computer needs to be retained for a longer period of time. Most laptops today are provided with power management features and software. Power management software can help in regulating the use of the battery and electric power. It monitors the load on the hard disk, the activities on the laptop and the ambient brightness, and changes various computer settings to make optimal use of power. This software also allows users to set timings when the computers can automatically go to standby or hibernate mode. For example, notebook computers can be set to go to standby mode after 20 minutes of inactivity or when the laptop lid is closed. This helps in automatically managing the power consumption of the laptops. Desktop computer. Desktops are personal computers that are meant for use from a single location and are not portable. Though these devices are being replaced by laptops, there are certain applications where these devices are still used, such as intensive processing applications, but not in a scale where servers are required, like image processing. The architecture and physical configuration of desktops support upgrading and replacing individual defective subunits and parts. Since desktops are quite rapidly being discarded in favor of laptops, the biggest problem facing the industry is disposing of or recycling these devices. In addition, quite a few desktop users are home users who are not fully aware of disposal mechanisms, unlike the enterprises that are obliged to safely dispose of their assets. A typical desktop uses about 115 watts of power. By US rates, if a 115 watts desktop is used continuously for one full year, it costs about $100, 8,760 hours, year times 115 watts times UST 0.10/kWh. Cathode ray tube, CRT, monitors were the primary output device used in desktop PCs until a few years ago. CRT monitors consume a lot of energy and are inefficient. A typical 17 inches CRT monitor consumes about 80 watts compared to 28 watts consumed by a 19 inches LCD, DisplayLink, 2008. It also contains a lot of environmentally sensitive materials. LCD and LED monitors are energy efficient, Robertson et al., 2012, and small in size. The power management systems and techniques for monitors that were described in Section 2.2.4.1 on laptops also apply to desktops. The processors used in desktops consume a lot more power than their laptop counterparts. The processor and hard disk power optimization techniques that were used in laptops also apply here. One of the areas where a desktop varies from laptops is in its mode of usage. Desktops are powered from external power, so, in many cases, they are kept always on so that they can be remotely accessed from a laptop or some other desktop. In most cases, desktops are left on 24/7 even during holidays. Hence, most of the time desktops remain idle and waste a lot of energy. To avoid having desktops switched on all the time, remote wake-up methodologies have been devised. In the 1990s, Advanced Micro Devices, AMD, and several other companies came together to develop the Magic Packet technology to accomplish this. It is commonly referred to as Wake on LAN, WOL. This relies on a special kind of packet called the Magic Packet to wake up the computer. When the computer is in sleep state, the Ethernet Network Interface Controller, NIC, is left powered on. This network interface controller can detect the magic packet and trigger an interrupt which wakes up the desktop. Using this technology, desktops can be awakened at any time from remote locations, thus removing the need to have the desktops switched on all the time. In enterprises, where there are many desktops in use, it is important to globally monitor the usage of all desktops to get a holistic picture on their usage efficiency. Tools like Night Watchman, www.1e.com, The Energy Detective, TED, www.thenergydetective.com, eMonitor, www.powerhousedynamics.com, and Conserve Insight, www.belkin.com. Weblink help managers in assessing the power usage trends of many of their desktops over time by monitoring these trends and presenting the data in the form of a dashboard. The dashboard helps managers understand the desktop's power usage patterns and set power conservation targets, which will make the company greener. Several online energy calculators are available, for example 1E, ND, which help in calculating the amount of energy that can be saved. In addition to monitoring tools, enterprises also need management tools which allow remote control of desktops. Though most operating systems have group policies which allow certain configurations to be enforced on desktops, they are not as effective as management tools which allow granular control over the desktops. Tools like Night Watchman help enterprises have more control over the desktops. These tools allow enterprises to securely, remotely and centrally power down desktops. They also allow enterprises to apply power schemes at different times in multiple locations, globally from a single console, maximizing power savings without impacting users. Though there might be resistance from employees to the implementation of such systems, it is important to make employees understand the benefits and advantages of the system and then implement solutions. Servers. Servers are computers designed to serve the needs of other computers. In general, server computers run one or more services that will be used by other computers in the network. They have powerful CPUs and a large amount of memory, RAM. They are generally placed in racks. Examples of servers are mail servers, database servers, file servers and others. They are on most of the time, and in most cases to provide increased reliability redundant servers are used. These servers are generally placed in data centers. Even though the growth of energy usage of data centers was less than predicted, Kumi, 2011, it still accounts for between 1.1% and 1.5% of total electricity use. Servers in general generate a large amount of heat due to their large power consumption, and hence they require better cooling mechanisms. Mobile devices. Mobile devices comprise mobile phones, personal digital assistants, PDAs, and other smart devices that people carry around. These devices are small in size and are powered by a small rechargeable battery. These devices are produced in large numbers and are designed for operation with low power consumption. These are used by people all over the world from both developed countries and developing countries. The International Telecommunication Union, ITU, estimates that by October 2010, over 5 billion mobile phones were in use. International Telecommunication Union, 2010. Mobile devices use external chargers for their batteries. The power efficiency of these chargers is low, and most people keep the charger powered even whilst mobile devices are disconnected after being charged. Chargers consume power even whilst not changing a battery and hence waste power. So, chargers should be switched off or unplugged when they are not charging, or disconnected from mobile devices. Awareness needs to be created among users to switch off chargers when they are not needed. Specialized devices. Specialized devices are designed for a specific purpose, such as set-top boxes, playstations and medical equipment like X-ray machines and computerized tomography, CT, scanners. Since these devices are designed to accomplish a specific purpose, the designer can optimize the device for the particular use and for low power consumption. Devices like set-top boxes and PlayStations consume power even when they are not in use, idle, and idle power could be as much as about 2/3 of the power the device consumes when it is used. For such devices, it is important to switch off the devices so that they do not consume, waste, power when not in use. PlayStations in general have powerful graphics processors which consume a lot of power. It is a common practice among users of PlayStations to leave them in pause mode for long periods of time, which results in power wastage. It is important to create awareness among users of special devices to switch them off when they are not in use. Reuse, recycle and dispose. Mobile phones and computers, as well as some other electronic gadgets, become obsolete quickly, typically about every 2 years, due to continued advancements in technology and the introduction of new gadgets with enhanced features. This leads to an accumulation of much e-waste. Most of these devices end up in landfills or get exported to developing countries for recycling. In many developing countries, however, due to lack of sufficient knowledge about the toxicity of the chemicals involved and lack of regulations enforcement relating to e-waste recycling, unhealthy recycle methodologies are used, leading to health hazards and pollution. One way to reduce waste is to increase the lifespan of the devices. Increasing the lifespan of devices saves life cycle energy and resources and reduces the amount of hazardous materials ending up in landfills. Reusing an old computer is a great way to increase its lifespan. Reusing a computer is environmentally friendlier than recycling. It has been shown that reusing a computer is 20 times more effective at saving life cycle energy than recycling. Computer Aid International, 2010. As there is a lot of environmental cost involved in a device's production, it becomes important to use a computer to its fullest life before discarding it. Once we have decided to replace a device, the first option to consider is to send the computer for reuse to some other place like an educational institution. Both the EPA in the United States and WEEE in the European Union provide guidelines on enabling computer reuse. Before sending the device for reuse, adhere to the following guidelines: U.S. Environmental Protection Agency, 2011. 1. Make sure that the receiving organization does need the device being sent and can reuse it. A better alternative would be to send the device to a local refurbisher who will make sure the device is in a working state and can send it to an appropriate organization that is in need of it. 2. Copy the information that has been stored in the device to a backup device or another device. 3. Wipe off personal or sensitive information in the device using tools specific for this purpose like Symantec's Wipe Info. Another way to increase the lifespan of a device is by enabling easy upgrade of its various parts. This will encourage people and organizations to use their device longer by upgrading certain parts of their device that have become obsolete. Some design considerations that enable the easy upgrade of a computer are as follows. 1. The device should be modular. 2. Each part of the device should be easy to replace. 3. The device should be easy to disassemble and reassemble. Techniques like screwless casing make it easy. Wherever reuse is not a viable option, the next best option is to recycle. In the process of recycling, most of the original device's materials are reused as raw materials for a new device, thus resulting in less waste. To enable recycling, it is important to collect back the old devices from customers. Many manufacturers have their own recycling programs. Take back, Mail-in and trade-in programs are some of the popular programs that encourage customers to return devices to the manufacturers. In addition, companies also support local organizations to collect the devices. In order to increase awareness, collection events and local recycling events are conducted. These programs help individual users easily recycle their computers. In 2009, the United States generated 3.19 million tons of e-waste. Of this amount, according to the EPA, 2011, only 600,000 tons or 17.7% was recycled. The rest was trashed, in landfills or incinerators. An electronic device consists of various materials which take quite a lot of energy to extract from ores. During recycling, these materials can be recovered, and some of the recovered materials can be used in making new devices, thus reducing the amount of environmental emissions compared to making these devices from virgin materials. Materials like gold, silver, copper and plastic can be recovered and reused. Some companies use a measurement called recycling rate, which is the weight of the materials the company recycles each year as compared to the total weight of the devices the company sold a few years earlier. As discussed in this chapter, one of the problems regarding recycling of e-waste is the export of e-waste to developing countries for recycling. Developed countries export their e-waste to developing countries since the cost of recycling is cheaper there. For example, recycling a computer in the United States costs about $20, whereas recycling a computer in developing countries like India or China costs only about $2. But e-waste is not properly recycled in developing countries. In many cases, the laborers involved in recycling simply burn off the e-waste, follow crude unhealthy practices to remove components and metals from e-waste, or dump the waste into rivers, resulting in huge environmental impact. They are unaware of the environmental and health hazards posed by the chemicals and poisonous gases released in the crude recycling process they follow. They are not required to wear protective clothing, and thus face severe health problems. Efforts have been made by organizations such as Greenpeace to regulate the export of e-waste to developing countries and to adopt healthy e-waste recycling processes. Whereas refurbishing and recycling are effective techniques for the end-of-life management of electronic devices, often they are not practical. The only option left at this stage would be disposal. There are a few known techniques of waste disposal that are commonly used in e-waste disposal as well. These are incineration, chemical decomposition and landfill. There is no single silver bullet that works in all cases for all materials or all kinds of e-waste. Incineration may result in the release of toxic gases and can pose a hazard. On the positive side, the heat generated may be used in generating electricity. Due to the non-biodegradability of materials used in electronic devices, landfill may not be a viable option either. Chemical decomposition may be an option in some cases and will have to be executed in a managed manner. In short, safe disposal is a major problem, and the solution depends on the specific material used in manufacturing the device.